the last 1 year. I began working with him from the spring 2014. And for my thesis, the area which I worked on was the evaluating the effectiveness of brain in localizing different types of software fault. So let me begin with the outline of.
So as I mentioned, time management is very important. Now 50 minutes has already passed. So I will set up the timer at 12, let's say, 45. You have to finish at 12:50. Okay. Have you finished your presentation?
By 12:50.
12:50. Okay.
So this is an outline what we are going to discuss today. So introduction, what we do, what is our experimental design for this work, and what are our results and conclusion. To begin with, let's start with fault localization because most of my work is related to fault localization. So debugging, when you say debugging is an activity in which it just refers to the activity of locating faults. When you perform testing, whenever you have a testing failure, the next step what you do is finding the bug. So when you say finding the bug based on the test case fails, you try to find out what is the root cause of your fail. That's debugging. Generally in normal software engineering activity, starting from analysis to deployment, debugging is one of the challenging and more time-consuming tasks, and it involves a lot of time and human efforts. So, automatic fault localization, which is based on test results, we tend to find bugs automatically based on the test output results which we find automatically will help us in reducing cost, efforts, as well as time. So there are among automatic fault localization, one of the approaches called spectrum-based fault localization technique. What we do in spectrum-based fault localization approach is like we compare the execution traces of a failed test case with that of a passed test case. So when we compare, based on our comparisons, we start ranking the statements based on their suspiciousness. I will give an example in the upcoming slides how this works. A couple of examples of tools which follow the spectrum-based fault localization is Tarantul or Nokia. This is an example from a paper. So this explains how a spectrum-based approach works. So if we consider here, we have 1, 2, 3, 4, 5, 6 test cases, and this is the line of code, and the bug is over here. So as a in spectrum-based fault localization, we compare the execution trace of a failed test case with a passed test case. Over here, these dots expire. These dots indicate the execution trace, in the sense like for this test case, these are the lines that got executed. For instance, for first test case, line number 1, 2, 3, 4, 6, 7, and 13 got executed. Likewise, for all the other test cases, indicates what are lines executed. Once we have this execution trace information, we can compare. We select the failed test case among all. So if you see here, this statement has one failed. We take the failed test case. We compare the statements, like we start with first statement. This statement was executed by failed test case as well as by all the past test cases. So as the second statement, so was the third statement. Whereas in this statement was executed by one failed test case and only 3 past test cases. So likewise, we compare all the test cases, and when we see statement number 7, it's being executed by failed test case and by only one past test case. So the number of past test case executing is less than it's being executed by failed test case. So the suspiciousness of this statement to consider to be faulty is very high. So the overall ranking is based like that. They compare the execution trace and rank this statement on based on the suspiciousness. We see here, for example, statement number 10 and 11 was not executed by failed test case, whereas it was executed only by past test case. So it indicates this statement does not contain a fault because after executing a statement, the test case has been a failure. based on this concept, they rank all the statements. So this statement was executed by failed test case and by only one pass test case. So this is ranked have higher score and ranked accordingly number one. If you take the second rank statement, again it's executed only by two pass test cases and one failed test case. So it's ranked number two. So this is a basic idea how a spectrum-based approach works. It compares the execution trace of a failed test case with a pass test case and determine the suspiciousness. So coming to the main thing, this Ben is a software for localization tool which closely follows the spectrum-based approach. Ben does fault localization by getting input. The input to this tool is an combinatorial test set with this execution tree test. What I mean is, like, we provide the combinatorial test set with the test results to the tool along with additional informations. Once it contains two phases. In phase one, we identify failure inducing combinations, and in phase two, we do the ranking of statements. The final output of Ben will be statement ranking, where the statements will be ranked based on their suspiciousness. But top ranked statements are considered to be highly faulty. I mean, more likely to be faulty. Sorry. And statements which are ranked lower are unlikely to be faulty. So Ben basically rank the statements based on faultiness. So if you have a statement ranked 1, it's considered to be highly faulty.
But you need to explain who developed it. Why do you want to explain?
So yes. So Ben is developed by Lale. She's from our lab. She works on a combinatorial test set, and it's from phase 1 till end. It was developed by her. We have a command line version as well as a GUI version of Ben. And this is an example of Ben, how it works. Let's consider this is a source code. So this example gives a high level view how Ben ranked the statement. In phase 2 of Ben, we have one failed test case and two passed test cases. So what Ben does is it compares the execution trace. If you consider this statement was executed only by the failed test case, not by the passed test case. So it's indicated over here. And this is what Ben does is, once it has its core member, we refer the failed test case as a core member and passed test case as a derived member. So what Ben does is it starts comparing the execution trace of core member with each of the derived members. So let's say Ben starts comparing this execution trace with the first derived member. And if the statement was executed by the core member as well as by the derived member, it's going to be 0.5. The reason being when it's executed by if I can find an example that here again it was executed by core member as well as the derived member, so the score calculated will be 0.5. If we come down further down, if you can see statement number 6, you have a statement which was executed by core member, which is failed test case, and was not executed by derived member 1, which is a passed test case. So when in comparing core member with derived member 1, this is highly suspicious, so it's ranked 1. Likewise, the ranking is being done. If we come over here to line number 13, and let's take line number 14. In case of line number 14, this line was not executed by the failed test case, whereas this was executed by the passed test case. So ranking, when I'm comparing the core member, the failed test case with the failed test case with the passed test case, it gets a rank score of 0. So once it then compares the failed test case with the first passed member, we have one more derived member, one more test case which results in a passed state. So it does the same operations over here as well. It starts comparing the execution trace of this failed test case with the execution trace of the second passed test case, and ranks accordingly. Once we have both the comparative ranking, then we tend to take the average of both. So here 0.5, 0.5, sum of the average of these two is going to be 0.5, whereas here the average of these two is 0.75. What it indicates is when you compare the first failed test, when you compare the failed test case with the first passed test set, the statement was not executed by it, whereas it was executed by the second passed test. So it has a score of 1 and 0.5, and eventually the overall suspiciousness score is 0.75. When we come to the statement number 9, it was not executed by both the test cases which result in a pass state, and it was executed by only by a test case which result in a failure. So it indicates this statement is more likely to be suspicious and more likely to be faulty. So this is ranked as 1. This is a overview how Ben works.
Yeah, just a comment. I want to make sure that you give enough time to talk about your work. So because time is very limited, so keep that in mind.
This is a basic. I didn't say indicator. This is a basic screenshot for a tool. This is phase 1 at the end of phase 1. We identify for this replace program. Ben identifies a suspicious combination. The next screenshot, it's the final ranking. It shows this ranking. These are the statements which are faulty. So this is just a snapshot how our tool works. So coming back to the main topic in my thesis. So Ben locates a fault, but what we are trying to focus is like trying to identify how the effectiveness of Ben differs in finding different kinds of faults. When we say different kinds of fault can have many properties. We focus on how these 3 properties of fault affect the effectiveness of Ben in locating a fault. So to begin with, I will explain you what are these properties in first place. Then we can go from there. So let's start with the first property called accessibility for a fault. Accessibility is defined as the degree of difficulty to reach the fault during the execution of the program. So I can explain this with an example which follows now. So let's consider a part of a program which has to apply a discount of 10% if so and so criteria is met. In this case, if the purchase is more than $1,000 and if member category is gold and he is a person, he will get a discount of 10%. And this is a logic to apply, which applies the discount. And we have a fault over here. Instead of applying as 10% discount, it applies as 1% discount. This is a fault. Now let's assume we test the program with these following test cases. The first test case is a purchase amount of $1,200, and the T represents the customer is a member and he belongs to an executive group. Whereas test case 5, he makes a purchase of $1,100 and he is a member and he belongs to gold group. So how we measure accessibility is like we run all the test cases on the program and we identify how many test cases can reach and execute that faulty statement, based on which we measure the accessibility.
But what properties you have behind for the test set that you use to measure accessibility?
Sorry, can you repeat the question?
Does the test set that you use to measure accessibility have to satisfy some properties? You cannot just take any test set to do this, right?
Yes. Yes, we cannot take any random. There is a property. We need to have test input values within our domain, whatever is accepted. Like for instance, like here I cannot pass some random values to make sure.
No. What I'm talking about is the test set that you use to measure accessibility. That has to satisfy a particular problem. Otherwise, the accessibility that you measure will depend on the test set. The accessibility is a property that depends on the program, should not depend on the test set that you use to measure accessibility. how you deal with that. So if you just pick any test set, right, the the um, the accessibility that you get will really depend on the quality of the test set that you have. Different test sets may give you different accessibilities, and that is not going to be. You have to somehow deal with this particular problem. You have to somehow make sure the test set that you use to do the measurement has to satisfy some properties.
One thing I could think of is in our experiments, we make sure the input values, whatever we provided for the test set, is within the range of the variable.
That's about the input modeling. I'm talking about the test set. In theory, you have to use exhaustive test set.
Oh, exactly.
Otherwise, the accessibility will not be, will be dependent on the particular test. That is the key point. Otherwise, it's not the right measurement, right?
Yeah.
And you cannot do that. Actually, you cannot always get a exhaustive test set what you do. You have to explain that. That is the key point. You cannot just, the point is that you cannot just take any test set to do the measurement. It's not going to work. Yeah, go ahead.
So, continue with how we measure accessibility. We check the execution trace of each test set, all the test sets, and determine how many test cases test set access the fault. In our case, only test case 5 access the fault, but 4 test cases never access the fault. So we measure the accessibility as just like number of test cases access the fault by total number of tests.
So I have a question. So until right now, my research is not in this direction, but I still didn't know what's the key problem. So what's for your thesis?
Okay. So
because I cannot get, you had talked a lot of things, but I want to know what's the key problem.
okay. So our main goal of this experiment for our whole thesis is like how the effectiveness of Ben differs in locating, how the effectiveness differs in locating a
How
fault.
to test the Ben, or how to,
Now, when Ben locates a fault,
okay,
we measure the effectiveness of Ben based on number of statements a user has to investigate to reach a fault. What I mean is like Ben gives us a set of statements rank number 1, set of statements rank number 2.
I actually slide 24.
Yes.
Is this your key problem?
Yes.
I think we can start from slides.
In the beginning,
Yeah. That's fine.
you make clear the problem statement. Okay.
Next property we define about is input value sensitivity. It's input value, if a fault is considered to be input value sensitive, means that this fault will not produce a failure for all the input values. It might produce failure for certain input values, but not for all. Again, I can go with an example about that. This is a program which does the addition of 2 numbers. The fault over here is instead of addition, it does a multiplication. So when we do the testing for this application, the fault is over there. So when I test the first test set, it creates a pass because 2 plus 2 and 2 into 2 is going to be same. So same. That is for the rest of the test sets. It fails because the fault multiplies rather than performing the addition. So this kind of fault we refer as input value sensitive because it produces failure only based on input values, not for all the input values. Which is a control flow sensitive fault. What we say as a control flow sensitivity is like a fault on execution will trigger a change in the overall program flow and still end up in a failure and will produce a failure. So to explain how we define a control flow and what is actually a control flow sensitive fault, let's take an example program. This generates what it does. This program, what it does is it's a simple program. It takes whatever input you give an input, which is an integer number, it will check whether the number is greater than 9 or less than 9 and print a message accordingly. So the fault over here is at line number 4. This is the fault. Instead of checking for numbers greater than or equal to 10, it prints only for greater than 10. So let's see how this fault induces a change in program flow. So if we have these test cases where test case 10, 1 and 2 have a value of 12, 5, and test case 3 have a value of 10. Only test case 3 will result in a failure. I'll show you why it fails. So this is the fault. We pass an input of 10. If the program does not have a fault, it's error-free version. These are the set of lines of code that should have been executed. Due to the fault, it induces a change in the program flow. Rather than executing line number 6, it executes line number 10 and still results in a failure. So these are the basic idea about what are the 3 properties. And to answer your question, this is the actual what we are doing. Like, we are trying to identify how these 3 properties affects the effectiveness of the fault localization code, which is plain. So to do that, first we performed our experiments on these subject programs. This is a Siemens, grep, and gzip, and we used this from this repository. And now, just a quick overview of what is our subject programs. So Siemens, if you take Siemens programs, Siemens soon has 7 different programs. This talks about the number of lines of code and each program has multiple versions, and it gives an idea, basic idea about the versions and the number of lines of code. Same with the.
So it would be better if you have shown the total number of versions that come with the Siemens programs.
So the same with the grep and gzip. So let's start with the actual work what we did. So to perform experiments on this set of subject programs, this is a step we followed. As Professor said, like, we need to have an exhaustive tester to measure accessibility. But in our case, we cannot create an exhaustive test set. So we went with a concept of random testing approach, which is like we generate a number of 1,000 random tests, and we run on all these random tests on our subject programs.
So the first step is it's confusing, right? So are you generating 1,000 test sets, or you are generating one test set, but it has 1,000 random tests?
Apologies for that. It's actually one random test set with 1,000, which contains 1,000 test cases.
So you need to change that.
Yeah,
The
sorry.
document it's not clear.
I'll do it.
Actually, what you write here is more like 1,000 random test sets. So you need to fix it.
So once we have the random test set, we execute the random test set on the subject programs. When we execute the random test set on the subject programs, we record the execution trace using a coverage tracking tool called GPA. Once we have the execution trace information, we will measure the accessibility, input value sensitivity, and control flow sensitivity property of the faults in the subject programs. So when we measuring the input value sensitivity and accessibility is pretty straightforward. About I explained in the previous slides, like we could use the execution trace information and figure out how many statements can access the fault, measure the accessibility, and you see whether a fail in a past test case, access the executed faulty statement, and you get the input value and sensitivity. But with control flow sensitivity, what we did is we executed the random test cases on the faulty version, captured the execution trace, as well as we executed the random test cases on the error-free version, which is non-faulty version, and captured the execution trace. And then we pick one test case which results in a failure and compare their execution trace with failed test case with the execution trace in the faulty version as well as in the free version. The idea behind doing this is when you compare, you get to know if there is any change in program flow. What I mean is, if there are certain number of statements which was not executed in the faulty version whereas executed in the free version, vice versa, and that is due to the fault. So that's how we determine the control flow
So
sensitivity.
you automated the process. You like how do you determine control flow sensitivity? Did you do it like manually, or do you have
I did it manually.
script to automate the process?
I did it manually for control flow sensitivity.
What about the input value?
Sorry, input value, accessibility, and control flow sensitivity. I did it manually for all the faulty flow.
Can you write scripts to automate the process?
It can do that.
Definitely more
Protective.
objective, because when you do it manually, it's easy for you to make mistakes, right? So that's something that probably you want to do after this. Okay.
So this is the overall results from our work.
So actually now you will check the results, right?
I checked for the graph,
Okay.
or GZ, one of those two. I don't
You
know.
also did it like manually,
Yes.
no scripts.
No.
So
The problem with the script is that different versions have different faults. So if you have a script, you need to specify which line is the faulty line.
Okay, but you can take that
Yes.
to your script.
It should be input.
So see, it should be possible to automate the process.
Yes, for input value sensitive and accessibility, it is very easy, I think. But for the control flow sensitive, it depends on how many different between the faulty version and the clean version we have. I want to say, for example, if you have one state, one inter, then the number of the lines are not matched. So it's not easy to compare which line is executed or not automatically. You need to first define which statement and then compare what's happening.
So you need to map between
Yes.
statements in the clean version and in the faulty version.
First and then compare whether it is executed or not. But for the input value sensitivity and accessibility, I think it's more easy.
Yeah, we should try to automate as much as possible, because when we report an experiment, it's very important for other people to reproduce the experiment. So you want to minimize the manual effort, right? Because that's not easy to reproduce.
So this is the overall results we had from our experiments, which says like there were a total of 126 faults, in which 78% of fault had a 78 versions had a fault which is input value sensitive, control flow sensitive, and have a higher accessibility. For likewise, if I take second one, there were 21 versions of fault which is input value sensitive, control flow sensitive, and low accessibility. Likewise, this table summarizes the overall results. Among all those 126 versions, we couldn't come across a single fault which is an input value and control flow insensitive and with a high accessibility. So this one combination of fault, we couldn't come up with on faulty version. Our main goal was to determine how input value sensitivity affect the effectiveness, how control flow sensitivity affect the effectiveness, and accessibility affect the effectiveness. So to do that, the approach what we followed was to determine how accessibility is going to affect the effectiveness of them. We fixed the other two values. When I say fixed, if you see this table, like here input value sensitive and control flow sensitive, both are constant. So if there is any change within the
5 more minutes.
or if there is any change within the effectiveness, then it's assumed like this should be because of the accessibility rather than the other two faults. So this is a basic idea. So with this, we started evaluating it.
So try to cover the most important points that you want to make.
So what's your conclusion?
Yeah, slides hang. So our conclusion is like, for instance, in the case of accessibility, the effectiveness of Ben is highly effective in locating faults whenever the accessibility is low. So whenever we have a low accessible fault, what I mean is whenever a fault is harder to access, like not all test cases can access the fault, Ben is effective in finding such kind of faults. So we did the same thing for rest of the other two properties, which is input value sensitivity and control flow sensitivity. In input value sensitivity, we got a mixed results. Like there are a couple of versions where Ben is effective when it is not input value sensitive, and there is one version where it is input value sensitive. So we are unable to reach a conclusion which one is the best, whether when Ben performs best, whether it is input value insensitive or when input value sensitive. But most of the cases, Ben has a better effectiveness in locating faults whenever it is an input value insensitive fault. The same goes with control flow sensitivity. There are cases where so this is the overall version of overall results of control flow sensitivity. Over here, there are times where there are a couple of sets where Ben is effective in locating faults when it is a control flow sensitive fault, but there is also an instance where Ben is effective in locating when it is control flow insensitive faults. So with input value sensitive and control flow sensitive faults, we are unable to reach a conclusion. So this is our overall conclusion. For accessibility, whenever Ben is actually highly effective in locating a low accessibility fault. The reason we believe is like whenever the fault is harder to access, it's more likely to be executed only in the failed test sets, and very less likely to be executed in the fast test sets. So since spectrum-based approach compares the execution phase of fail and pass and rank the statements, these faults get ranked the top, whereas Ben is not highly effective in locating high accessibility fault, because there are chances of high accessible fault appearing in both the failed test case as well as in the past test cases are high, because so more likely to be executed by both failed and passed. So Ben ranks number one. This is the conclusion about the impact of accessibility on the effectiveness of Ben.
I think to be fair, that also has to do with how Ben actually works, because like can you go back to the previous slide? Like the ports that are harder to access, if they have a no accessibility, that means, I mean, for both failed and past test cases, they are difficult to be executed, right?
Yes.
And the reason why Ben is more effective for low accessibility faults has to do with how Ben works, not only because like in general, no accessibility faults are likely to be executed only in the failed test cases. Because if you look at the definition of no accessibility faults, it's basically more difficult to be executed, no matter it is a failed test case or it is a past test case. So I guess the point is that the explanation has to do somehow with how Ben works, how it derives like a core member and derived members, not only because what you have here.
Okay. So with input value and control flow sensitivity, most of the results indicate it's Ben is effective in locating input value insensitive and control flow insensitive faults, but we are unable to reach a conclusion. In future, we were planning of evaluating the effectiveness of this approach in locating real-time faults. In addition to this, I would like to add a couple of things. One is automating finding the properties. This one I will add it in the future work as well. Like what Professor suggested, like automating the whole manual process involving these experiments.
What do you mean by locating real-time faults?
Like these are all seeded faults, like, like whatever we tested till now, are like seeded faults.
Is that supposed to be a separate sub-bullet from the first one, or is part of the first one?
That's what it is.
So are you supposed to have like two sub-bullets or just one sub-bullet? You have two lines of. I guess my question is that is locating real-time faults part of the first one, or is a separate
It's
direction?
part of the first one.
Part of the first one. Part of the first bullet, sub-bullet, more empirical studies to evaluate.
So, I mean, what I'm trying to say is, like, till now we focused on finding the effectiveness in a seeded fault. If in future we focus on doing experiments to finding the effectiveness in locating real-time attacks.
Real-time faults, what do you mean by real-time? Do you mean like real-life faults or real-time faults?
Okay.
What do you mean by real-time faults? That's my first time for me to hear this term.
These are all, when we just seeded faults, we manually manually create a fault, and in a sense, I mean, every fault is manually created, but what I'm trying to say is, like, it's not like seeded fault. You know, in seeded fault, whatever we had for CMOS and seeded faults.
You know where the faults are. That's
Yeah.
what you are trying to say. And so what you really trying to say, like real-time faults are basically real-life faults that you may not even know where the faults are, right? But if that is the case, how can you evaluate the effectiveness? So you remember what you are doing is to evaluate the effectiveness of a fault localization technique. It's not about how to apply a fault localization technique. So for the evaluation purpose, you would have to know where the faults are. Otherwise, how do you know whether you have effectively located the faults or not?
Okay. So, what was my thought process was non-seeded faults. I'll correct it.
Okay. All right. Okay. That's it. That's the last one. Last slide. I thought you had more slides. Okay. Questions? Maybe you want to ask Professor Chen first to see if he has any questions.
Professor, do you have questions?
Yeah, yes. I think the main conclusion of your work is that you believe that all hard access is likely to be executed only in the failed cases.
Yes.
And that's when the talk, right?
Yes.
First of all, I think I actually feel quite well about how you answer Dr. May's question. He said, since I have a little bit trouble with how to measure the sensitivity protocol, it's highly dependent on the test cases you design, right?
Yes.
And this is the first question which bothers me. Second, I don't see why. Can you explain why you make that conclusion, even if the accessibility is very low? I still can see why once it gets access, the chances for fail will be high. I couldn't connect the two. Can you answer this?
So to begin with, if I rephrase the questions, first question was like regarding the conclusion about the accessibility. Is that correct?
Yes. How you test? How do you know it's like you generate example like the test cases, right?
Mm-hmm.
So how can you be so
The question is basically how do you measure accessibility?
So how we measure accessibility is like, in our case, number of test cases execute the fault. It's a ratio of number of test cases execute the fault to the total number of test cases in the exhaustive test set.
Yes, but how do you define the test cases will affect actual accessibility, right? Like the one you showed in one of the slides I saw, you have this like $1,000 something like this, right? Example.
Yes.
So if you use if your test cases all have like the purchase of about $1,000, then the accessibility will be extremely high, right?
Not only $1,000, for that example,
Yeah.
there will be a couple of more other criteria, like the membership type has to be gold for that specific example.
Right.
The general question, I think, is similar to what I asked. So Professor Tse is asking how you can make sure the measurement is objective, because it seems like it really depends on what kind of test set you are using to measure the accessibility. What kind of test sets that you use to make sure the measurement is actually
We
objective?
use an exhaustive test set.
Right.
Yeah,
Maybe Professor didn't hear.
We use an exhaustive test set for this to measure accessibility.
Exhaust.
So we
Okay, we exhaust. Understand that.
So we created we cannot have exhaustive test set for our experiments, so we went with the approach of generating random test set, which
Okay.
and those generations is based on the input parameter models of our subject programs.
So you just randomly generate all kinds of cases.
Yes.
Right? Okay.
That's the key point, because in theory you need to use exhaustive ones, but you cannot use exhaustive ones, so you generate random test sets to represent the exhaustive test space.
Right.
That's the key point that we are looking for.
Okay, how about the second question?
Can you please repeat the second question?
The second question points to your main conclusion.
Accessibility.
That the faults that are found in the test only in the failed test. So it's not
So
that it's help you or
okay, so in Ben actually works in two phases. In first phase, we identify the suspicious combinations. In phase one, when you say suspicious combinations, we identify combinations which likely, whenever those, let me repeat this, we identify combinations which are those, whenever they appear in a test case, they result in a failure. So because of this approach, this harder to access fault should be, most likely will be in the core member.
Can you repeat it?
Okay, so in Ben, meaning the fault localization, the first phase, we identify the suspicious combinations which actually creating a failure, which is actually causing a failure. And these suspicious combinations, these inducing combinations will be part of the core member, which is a failed test case. So at the end of phase one, we will have a combination. At the end of phase one, we will have an inducing combination which will, we will generate a, let me say like this, we will generate a core member in phase two, which is almost certain which will execute this faulty statement.
Okay. but does it explain I don't see it answers my question here.
Okay.
So I understand what you're saying, but I don't know how this answers the question. As to if sensitivity is small, then once you make it sensitive, failure will be high. That's my question, right? I think that's the main conclusion of the work. Hello?
Yeah, I'm.
Sorry,
It's okay.
someone phoned me to interrupt. That's okay. Now it's okay.
So it's like, can you provide the answer now, or if not, probably you have to go back and get back to
I'll
Professor later about the explanation. That's also one of my questions as well, because you have to be able to explain why you have this result, and what you have here is not sufficient.
Okay, I'll get back to this on later, Professor, with a detailed explanation. Please.
Yeah, I don't think you can explain that clearly at this point. Okay. Okay. Do you have any questions? No? Do you have any questions?
What kind of tool you used for your combinatorial testing for generation of 1,000 test cases?
Okay, that's a good question. So we have a tool developed in our lab. It's called Axe tool. It is used to generate the combinatorial test set.